Good morning, Professor and classmates. Thank you for being here today. My presentation is about comparative analysis of zirconium dioxide sintering. We compare two massive PVD and CVD. We will look at their structure and thermal properties to see how good they are as various coatings. And here's piece of my talk today. First, I will introduce the background of our study. Second, I will explain the method we use and how we prepare the sample. Third, I will show you the characterization and properties of the film. Finally, I will talk about the thermal performance and give our conclusion. And this being with the introduction and background. So in the plastic injection molding industry, making very small micro size part is a big challenge. The hard melted plastic cool down too fast when it touches the closed node. So this fast cooling has defects and poor quality. So to solve this heat loss problem, we use thermal barrier coating or TBCs by applying a coating. Then we can reduce the heat transfer between the plastic and the mold. So this keeps the mold surface hot for a short time, so which improves the quality of the plastic parts. And why do we choose zirconia dioxide for these coatings? There are several good reasons. First, it has low thermal conductivity. This means it stops heat from passing through very well. Second, it has high mechanical strength, and it is very tough and durable. Third, it has a great corrosion and chemical resistance. So it protects the steel most from water and chemicals. And finally, its thermal expansion is similar to steel. So this means it will not crack easily when it gets hot. So all these points make zirconium dioxide ideal for injection molding. And the main object of the research is to directly compare two deposition methods, PVD and CVD. And we did a compare information. We checked their morphology, crystal structure, chemical makeup, adhesion, and thermal exclusion. So our goal is to find out which coating process is the best of thermal barrier on steel mold. And now let's move to the part 2, method and sample preparation. So we compare two different deposition methods. The first one is PVD magneton spotting. And this method uses a zirconium target in argon and oxygen gas. So the temperature is 200 degrees Celsius. And the pressure is very low. And the coating speed is slow, about 1.6 nanometer per minute. And the second method is the ELI and OCVD process. And this method uses a liquid zirconium precursor mixed with oxygen. And the temperature is much higher, between 520 and 550 degrees Celsius. And the pressure is also higher. And the coating speed is much faster. For CVD methods, and we also add a thin aluminum oxide sublayer. So this protects the steel from rusting during the high temperature process. And for our sample preparation, and we made different thickness to compare for PVD. And we made samples that are 17, 20, and 14 micrometers thick. For CVD, we make samples that are 4.5 and 17 micrometer thick. So to make sure our compression is fair, all coating will apply on the same type of steel structure. So by testing similar thickness like the 17 micrometer samples, and we can have a meaningful compression.
Section 3. Let's look at the part 3, characterization and properties. Morphologic. First, we look at the filling morphology and the structure using a microstructure. We found that both PVD and CVD filling grow in cool shapes. However, they look very different. The PVD fillings have a very dense and smooth structure. They have almost no holes. On the other hand, the CVD filling have a porous tree-like chromal structure. They have many tiny holes. Also, in thicker CVD filling, there are even more holes near the top surface. These holes are actually very helpful for blocking heat. Roughness. Next, we measured the surface roughness. The PVD 17 coating has a smooth surface texture. Its roughness value is 313 nanometer, but the CVD coating are much lower. The CVD 17 has a roughness of 1156 nanometer, and the CVD 4 is 542 nanometers. The reason for this high roughness is the porous tree-like structure of the CVD fin. Even if we divide the roughness by the thickness, and the CVD coating are still much rougher than PVD. Crystal and composition. We also test the crystal structure and the composition. The XRD test shows that the dominant crystal phase in the XRD text shows that the dominant crystal phase is monoclinic for all samples. The PVD 17 and the CVD 17 samples showed very strong monoclinic peak. The thinner CVD 4 sample also had a tiny bit of cubic phase. For the chemical composition, we found that all fins are very close to per zirconium dioxide. The CVD coating just have a very small amount of carbon. This is normal and comes from the liquid precursor we use. Adhesion. Another important property is adhesion. We want to know how will the coating stick to the steel. We use a scratch test. When we push hard on the CVD coatings, we saw some vertical cracks and a little bit of chipping on the side. When we test the PVD 17 sample, large pieces fell off. This shows the PVD fin has higher internal stress. But the most important finding is that both PVD 17 and CVD 17 started to fall at the same force. 27 newtons, and this means that even though the CVD structure has many holes, its machining strength is still very good. Section 4. Finally, let's discuss part for thermal performance and conclusions. Thermal extrusion. To test the thermal extrusion performance, we built a constant device with a hot cooper insert. The results were very clear. And all zirconium dioxide coating provide better thermal extrusion than bare steels. We also found that thinner coating block heat much better. If we look at the key result, the simple PVD 14 reduced the temperature by 9.8 degrees. CVD 17 reduced it by 6.5 degrees. PVD 20 by 4.6 degrees, and the CVD 4 by 1.2 degrees. Efficiency, but thickness is not the only important factor. Let's look at the efficiency per thickness. This table compares the thermal gradient, which means how much temperature is reduced per micrometer. You can see that CVD 17 has a value of 0.13a. PVD 40 only has 0.25. This proves that the CVD coating is much more efficient at blocking heat than the PVD coating for the same thickness. Summary. In summary, here are our key takeaways. First, both PVD and CVD mousts can produce effective thermal barrier coatings. Second, the microstructure drives the performance. PVD makes dense and smooth coating, which allows us to make them very thin. CVD makes porous and rough coatings, which give better extrusion efficiency per micrometer. By understanding and controlling the deposition process, we can optimize the porosity and create the best zirconium dioxide coating for our specific needs in injection molding. Thank you for attention. I am happy to answer any questions.